the students are around.
Good morning, sir.
Good morning. Okay, so can you see the presentation? Hello.
Yes, sir. It is.
Okay. So in the last class, we started looking at the concept of heat transfer coefficient. The reason behind that was we argued that conduction is in most of the cases associated with convection, isn't it? So this is one more additional difficulty we have added. So as you are aware that we are keep on adding our complications in our analysis. So the heat transfer coefficient basically gives us the heat transfer which is taking place in a convection mode when there is a fluid is there. Okay, so again we argued that conduction mostly takes place when the system is at a stagnant phase, isn't it? But whenever we are looking at the fluid, it hardly remains stagnant, even though a thin layer which is very close to the solid surface more or less remains in a stagnant phase. So based on that, the concept of conduction is applied to that particular film, and then based on that we have correlated how heat transfer coefficient is related to the thermal conductivity. This is what we have seen, isn't it? Again, assuming that this particular film is stagnant, that is the assumption. In real situation, there is no stagnant film. There is always a movement taking place in this film. Okay. So thereafter, what we started looking at is the heat transfer between the fluids separated by a plane wall. So here we have looked at there is a convection heat transfer taking place in addition to the conduction, and in all such cases we in general use the overall heat transfer coefficient, isn't it? So the concept of overall heat transfer coefficient we have seen. So overall heat transfer coefficient which also accounts the convection at both the sides of the solid and the conduction in between. Again, some of these factors we may neglect depending on which resistance is dominating. Okay, correct. Again, we have extended our analysis to a cylindrical surface when the area is not constant. In such cases, the heat transfer coefficient is again the overall heat transfer coefficient is again defined either in terms of inside surface area or outside surface area, because the area of heat transfer is changing, isn't it? So heat transfer coefficient in terms of the outside surface area is shown by this equation, and similarly for the inside surface area we have the another equation. Here you can note down that u naught a naught is same as ui ai. Okay, again some of the factors here can be neglected depending on which resistance is dominating. For example, if a gas phase is there outside, in such cases that resistance is going to be the most dominating compared to if there is a metal wall in between. So the resistance corresponding to the conduction through this metal wall can be safely neglected, so this middle term can be omitted. Also, if we consider that the resistance inside the pipe is also negligible, in that case this first term can also be neglected. So this happens when we are having a liquid flowing through a pipe and the pipe is a metal pipe and outside there is a gas. In such cases the most dominating resistance is the resistance offered by the film in the gas phase, because the thermal conductivity of the gas is going to be much lower compared to the thermal conductivity of the metal as well as liquid. Okay. So based on this, one of the tutorial problem also we have solved. Then we extended on looking at the heat transfer from the extended surface. So as we were arguing that whenever there is a gas outside, the resistance offered by the gas film is going to be the significant. So can we improve the heat transfer rate? So heat transfer, see here we cannot increase the thermal conductivity of the gas. We can increase the turbulence, but then there is also a limitation on that because external power is required for that. So the another interesting thing is to have a extended surface in which instead of increasing the heat transfer coefficient, we are looking at increasing the heat transfer area, isn't it? So we can have a higher value of Q either by having a higher heat transfer coefficient or by having a higher heat transfer area. So this idea of extended surfaces or fins is based on this particular concept, where instead of increasing the heat transfer coefficient, rather the heat transfer area is increased by having the extended surface area. So this particular case also we have obtained the generalized expression. So this is the generalized expression which we have obtained. Q is given by this equation BW K zeta TW minus T naught in the bracket sine hyperbolic epsilon L plus H by K epsilon cos hyperbolic epsilon L divided by cos hyperbolic zeta L plus H by K zeta sine hyperbolic zeta L. So this is a generalized expression. Similarly, the generalized expression for the efficiency is also obtained here. I will not go in the detail that anyway we have gone through in the last class. I am just summarizing whatever we have done here. But there is another interesting assumption people use. The another interesting assumption is by the time we reach to the end of the fin, all the heat that is being conducted towards the end is already been exhausted by a convection. So that is the assumption, that is a realistic assumption, because fins are designed in such a way that by the time it reaches to the end, it should be already dissipated, isn't it? So with this assumption, the second boundary condition in this case changes. X equals to L, we have minus K dt by dx. So that means the heat conducted or heat conducted from the solid at the end should be equal to 0. So if we put this assumption, we get a much simpler expression for Q. So this is the much simpler expression for the Q, and similarly the expression for efficiency we have obtained, that is tan hyperbolic zeta L divided by zeta L. So this is the simplest expression. In fact, if you look at many heat transfer books, you will find this particular equation rather than the previous one. Previous expression is the more generalized expression when we are not assuming that the heat taken by the conduction at the end is not equals to 0. There we are assuming that the convective boundary conditions, isn't it? Okay. After that, we have looked at the concept of critical insulation thickness. Here we have argued that when we are putting the insulation, as we increase the insulation thickness, the rate of heat transfer initially it increases and then it decreases, because as the heat transfer area increases, the rate of heat transfer by convection increases, isn't it? So in some cases you will see the rate of heat transfer first increases and then decreases. So this particular radius is called as a critical insulation thickness. One need to have a insulation thickness beyond this. If we have a insulation thickness less than this, rather than decreasing the heat transfer, we will end up with increasing the heat transfer. Okay. But it is not necessary that you will get this maxima always. In some cases you will see that there the critical insulation thickness does not exist. If you calculate K by H naught, if K by H naught is less than Ri, in that case the critical insulation thickness does not exist in such cases. Okay. The next concept which we looked at is the optimum insulation thickness. So by this time we have seen that the critical insulation thickness, then we have extended our analysis further, where we are saying that since beyond the critical insulation thickness, as I increase the thickness of the insulation, my heat transfer rate is going to decrease, but I cannot go ahead with very large insulation thickness, because that is going to incur cost, isn't it? So I have to find out a thickness of the insulation that will give me the best return, isn't it? So I should not be using the insulation thickness too high in order to have a very high capital cost, isn't it? So here there are two factors: how much energy saving I am getting by putting the insulation. This is one factor, and the another factor is what is the cost of insulation. So based on this, the cost function is formulated, and this cost function, this is the cost function which we have obtained over the service life of the insulation, isn't it? And then we can differentiate this cost function with respect to the outer radius, because outer radius is going to give me the insulation thickness, isn't it? Ri minus R naught is going to give me the insulation thickness. So Ri is anyway is fixed, because that is the radius up to the metal wall, whereas R naught is something which you are varying beyond Ri, isn't it? So you wanted to find out R naught minus Ri such that your return is going to be maximized or your cost is minimized. So here the cost function dpt cost function is differentiated with respect to R naught. So dpt by dr naught equals to 0. So here you can see the P2, which is nothing but the cost corresponding to the insulation. As you increase the insulation thickness, this cost is going to increase. As you are going to increase the insulation, P1 is going to decrease. So P1 is nothing but the saving because of the cost, because of the heat lost, isn't it? So heat lost is going to decrease as you increase the insulation thickness. So clearly, by considering both the factors, there exists a optimum insulation thickness here somewhere where my cost is minimum. So this particular insulation thickness is referred as a optimum insulation thickness. So we will see a tutorial today on this. Okay. So this was the quick recap of what we have done so far in this particular chapter. So let us look at the last topic of this particular chapter. So again, here we are looking at the same example which we have seen earlier. So we have looked at the electrical wire which was conducting the electric current, and because of resistance the heat is generated inside the wire, and this heat is getting dissipated along the radial direction, isn't it? So there is a insulation outside the metal wire, primarily to avoid uh, the uh, the leakage of the current basically, but this also act as a insulation for heat. Okay, so again in the conduction chapter, what we have said that outside temperature, here we have looked at T naught, and based on that we have solved everything. We said that outside of this insulation there is a temperature T naught, but that's not the realistic case. In a realistic case, what is going to happen is outside of this metal, the electric wire, outside of this insulation, there will be a convection taking place from the surface of the wire, isn't it? In the last analysis, when we have looked at the conduction chapter, there the concept of convection we have not looked at till that point, and therefore we have assumed the temperature here at the surface as T naught. But this temperature, uh, that analysis is not completely correct, because outside the surface there will be a convection taking place. So the additional factor of convection is present outside this, isn't it? So the boundary condition which we have looked at T R equals to R naught, my T will be T naught. That particular boundary condition is not correct. Instead of that, we should have at R equals to R naught, I am going to have convective boundary conditions. So at R equals to R naught, minus K dt by dr, that should be equals to H T naught minus H T Tc minus T naught, isn't it? So that is the convective boundary condition we have to include. Okay. So let us look at this particular problem again with this additional and more correct boundary condition. We have not looked at this particular boundary condition at that point, primarily because till that point the convection we have not included. We have not covered the convection, and that is why we kept our analysis simple at that time. Okay. So now again I am starting with the same final expression. I am not deriving this expression. We have anyway derived equation number 1 and equation number 2. In this particular case, again just to give a recap, there is a electrical wire conducting the current. Heat is generated because of the resistance, and the heat is dissipated along the radial direction. There is a insulation of thermal conductivity Kc. Thermal conductivity of the metal is Km, and there is a heat generation taking place which is accounted through a volumetric rate of heat generation psi V. Outside temperature of the ambient is T naught. H naught is the heat transfer coefficient outside, and the length of the wire is L. Okay, so these are the information given. In this case, since as we move along the radial direction, my area is going to change. Also, there is a generation term. Even though we are not including the accumulation term here, still one need to make a shell balance. So by making a shell balance, the final expressions which we obtained are Tm is given as minus R square psi V by 4 Km plus C2. This is the first equation which we have obtained. Here again, here the constant C1 will be there, but that C1 comes out to be 0. Okay, that is what we have seen. So these are equation number 1 and 2. I am directly taking from the analysis which we have done during the conduction chapter, in the conduction chapter. Okay, is it clear to everyone? Hello?
Yes, sir.
Okay, these are the same expression. I can go back to the conduction slides and I can show it, but you can take my word and consider that these equation 1 and 2 are correct. Okay, is it fine? Or you want me to show the derivation of this? Anyway, we have done it earlier.
No, sir, it's fine.
Okay. So the distribution of the temperature along the radial direction in the metal can be given by equation number 1, and similarly the distribution of the temperature across this insulation is given by equation number 2. Again, here you can see the constant C2, C3, C4 we have to find out, isn't it? So the boundary conditions here are at the inner surface of the insulation where R equals to Ri. When R equals to Ri, that is the boundary of the insulation here. At this location, my temperature Tm should be same as Tc. That is the first condition. Tm should be equals to Tc. And another condition that is there is whatever the heat conducted at this boundary should be same as the heat conducted inside the insulation here. So minus Km dTm by dr should be equals to minus Kc dTc by dr. So this is the continuity equation, isn't it? So we are assuming that there is a continuity of heat transfer taking place exactly at the boundary. Okay, so this is another condition. And the third condition which we are having is at R equals to R naught. So at R equals to R naught, we are having minus Kc dTc by dr. So that is the amount of heat conducted at the surface here should be same as the heat taken out by the convection. So that becomes H Tc minus T naught, where Tc is nothing but the surface temperature here at the wall. Okay. So now let us apply both these boundary conditions and simplify our equation. So from 1, 2 and 3 again at R equals to Ri, since we are assuming that at R equals to Ri, Tm equals to Tc, so this becomes Ri square, this becomes C3 ln R, and this should be equal. So this particular factor is equated to the second factor. That is what is being done here. Okay. Okay, so then again from the second expression, here minus Km dTm by dr, so we can differentiate it with respect to R, and similarly we can differentiate second equation with respect to R, and then find out the values at R equals to Ri and equate based on this. So that is what is been done in equation number 6. So from equation number 6 what we get is C3 is obtained as minus Ri square psi v by 2 Kc. So these equations are also same as what we have seen earlier. Okay. Now apply the second boundary condition. Now second boundary condition is Kc minus dTc by dr at R equals to Ri should be equals to H Tc minus T naught at R equals to R naught. So that is what is been done here in equation number 7. So if you put all the values here, again this Tc, if you look at from this equation, Tc is given as C3 ln R plus C4. So that we can put it in terms of R equals to R naught. Okay. So after rearranging, what we get is C4 is obtained by equation number 8, which is given as T naught, plus Ri square psi v divided by 2 Kc in the bracket ln R naught plus Kc divided by H R naught. Now put 6 and 8 in 5. So this C3 and C4 we can put in equation number 5 and we can find out C2. So C2 is obtained using this equation. C2 is given as T naught plus Ri square psi v by 2 in the bracket 1 by 2 Km plus ln R naught by Ri divided by Kc plus 1 upon H R naught, and we can put this C2 in the original expression. The original expression here in equation number 1, we can put C2 here and we can find out the distribution Tm, and similarly C3, C4 we can put it into and we can find out Tc. So that is what is been done. So Tm is obtained by using this equation by putting the C2 in equation number 1. So this is the expression. This is slightly different equation than what we have obtained earlier in the conduction case. Okay. Further, the Tc is obtained as T naught Ri square psi v divided by 2 Kc in the bracket ln R naught by R plus Kc by H R naught, and in this case psi v is given by I square rho divided by pi ri square L, where rho is electrical resistance per unit length of the wire. Okay. So this is the end of this particular chapter. Based on this, there are some problems solved in the book. Please go through those problems. Okay. So we continue with the next chapter. Let me close this and share another slide.
Sir, please upload this presentation today.
I have already uploaded. I have already uploaded just 3-4 days before. I have already uploaded this. Okay. Anyway, so let us move to the next chapter. Okay. Okay. So are these slides visible? Hello?
Yes, sir.
Okay. So now we are moving to another, interesting concept. Remember, we are slowly, extending our horizon of analysis. So now we are looking at the forced convection, isn't it? So up till now we have looked at the heat transfer coefficient. Now based on that, now we wanted to include the forced convection. Okay. So before we start the forced convection, let us look at some information about it. Why forced convection and how to deal with the forced convection when we are having a heat transfer by forced convection. Okay, so in case of convective heat transfer, it is not difficult to make a differential heat balance over an elementary volume. Okay, considering all kinds of the factors like what are the input, output, generation, accumulation, etc. Because that is going to give me the differential equations or partial differential equations, and that governs the distribution of the temperature in the medium. That is not the difficult part. Modeling is not a difficult part. Sorry. Okay. So what I am trying to say here is, if I have to make a shell balance, or I have to find out the model or the expressions, that is not a difficult part. I can make a shell balance and find out the complex differential or partial differential equations by making a shell balance using different factors like input, output, generation, accumulation terms, etc. The most difficult part is rather solving these equations, isn't it? Formulating is not difficult. Formulating, you can do it. In fact, you can see the Navier-Stokes equation. You can formulate easily, isn't it? The real challenge is to solve these differential equations. There, the difficulty is arising. So, in most of the practical cases, it becomes a formidable task to solve such equations for the calculation of the heat transfer rates. So calculation of the heat transfer rate by solving this equation is the difficult task. Even though the computational resources are growing day by day, but still solving a Navier-Stokes equation is complete Navier-Stokes equation is still a difficult task, isn't it? People generally solve a Navier-Stokes equation by making the assumption whether it's a inviscid flow or whether it is a viscous flow, isn't it? Based on that, some of the terms get cancelled out and then you solve. So the point here I wanted to make is even solving the Navier-Stokes equation is difficult, isn't it? So forget about the energy balance in this case, isn't it? Okay. So how people are doing. So since it is challenging to solve the partial differential equation, that doesn't mean that the people have stopped analyzing the heat transfer in the process applications, isn't it? So they have done something. So what people have done so far? What people have done, instead of solving the differential equations, what people have done is they have used the correlations in terms of correlations in order to calculate the heat transfer coefficient, isn't it? So what these correlations are? These correlations are based on the experimental data. So they have performed several experiments. They have performed the experiments over the large range of variation in the parameters. And based on that, they have obtained the correlations. Again, whether these correlations should have some, you know, uh, uh, physical significance or not, how that correlations should be, that part we will come to. But what I'm trying to say here is people have made different correlations, and based on these correlations they have calculated the heat transfer coefficient, and that heat transfer coefficient they have directly used in calculating the heat transfer rate. Remember, here the heat transfer coefficient H is a function of velocity distribution, is a function of heat transfer, thermal conductivity, density, specific heat. All these parameters are incorporated directly in a heat transfer coefficient, and this heat transfer coefficient is calculated using the empirical correlations. So what we are doing in a way is we are circumventing the solving of velocity problem. We are not solving the fluid problem at all, isn't it? So my job becomes extremely simple because I got H directly without solving the momentum transfer, and using this H now I can put it in the uh, Newton's law of cooling and then calculate the Q directly, isn't it? Clear? Now, as I said that the heat transfer correlations are used here to calculate the heat transfer coefficient, and these are based on the experimental results. So these are also associated with error. So usually if you look at the amount of error that is associated with these correlations is around 25 to 30%. Okay, so there is a 25 to 30% error is there in your prediction, but the point is you can still predict the heat transfer rate in the same order of magnitude, nearly the same order of magnitude, even though it might not be exactly correct. Okay. What should be the form of this correlation? Is there any physical, principles behind it? That we will see slowly in this particular chapter. Okay. Okay. Now another important thing is, so although the simple way to visualize convective heat transfer to or from a surface is to assume the existence of a stagnant film at the wall, no such film does exist in reality. So what we are saying here is, if you wanted to look at how the convective heat transfer takes place, that can be analyzed in terms of the film, a small film which is close to the surface, and then we can assume that the maximum conduction resistance is present in this particular film, and based on that we can find out how H is related to K, isn't it? That is what we have seen in the last chapter. But in reality, no such film exists. There is always a motion of the fluid is present in this particular film. This film is not stagnant. This film is not stagnant. Okay, so in most of the cases, it is true that the the resistance predominantly is offered in this particular film, which is very close to surface. So resistance is offered by a narrow zone of fluid near the surface called as boundary layer. Okay, but the fluid in this zone is never stagnant. So what we are saying is concept of boundary layer is important, because why it is important? Because most of the heat transfer resistance is going to present in this particular boundary layer. Okay. So so one of the simplest way of analyzing the convective transfer is to look at the boundary layer. concept of boundary layer, and based on that we can see how the convective heat transfer takes place. Okay. The concept of sorry sorry okay, the concept of boundary layer is of vital importance in understanding the flow and heat transfer characteristic near the wall. Okay, that I have already said. Okay. Now let us look at the concept of boundary layer. So we are considering a simple case. We are considering a simple case where there is a flow of liquid taking place over a flat plate. So there is a flat plate and the flow is taking place here. So the velocity here is uniform, which is a free stream velocity equals to V. So when the fluid touches at this particular edge here, the velocity at this surface becomes 0. So that is the no slip condition. And then the velocity is distributed something like this here. As we move from this leading edge, as we move along the x direction from the leading edge, the thickness of this boundary layer increases. So here the thickness of the boundary layer is 0. As we move along the x direction, my thickness delta x is going to increase. So initially my boundary layer predominantly stays in a laminar region. So up to this there is a laminar region. Up to this there is a laminar region. From this to this there is a transition region, and beyond this there is a turbulent layer. Whether my boundary layer is lying in a laminar region, turbulent region, or a transition region is obtained or can be evaluated using the Reynolds number, and the Reynolds number in this case is defined in terms of the distance x from the leading edge. So what is the distance x from this leading edge here? That defines the Reynolds number, and therefore this Reynolds number is given as Rex. Here X is corresponding to the fact that the Reynolds number is calculated in terms of this distance x from the leading edge. So Rex, which is nothing but the Reynolds number in terms of this x distance from the leading edge, is given as rho Vx by mu, where rho is the density of the fluid, V is the velocity of the fluid, x is the distance from the leading edge, and mu is the viscosity of the fluid. Okay. So whether my boundary layer is going to be there in a laminar region is decided by the Reynolds number. So if the Reynolds number is less than 5 into 10 raised to the power 5, then my boundary layer is in a laminar region. When my Reynolds number is between 5 into 10 raised to 5 and between 10 raised to the power 6, my boundary layer is in a transition region. So this is the transition region which I have shown here. This is the transition region. And when the Reynolds number is greater than 10 raised to the power 6, my boundary layer is going to be there in the turbulent zone. Again, these Reynolds number and whether it is going to be laminar, transition zone and turbulent zone, these are given for this plate, flow over a flat plate. If you look at flow over a cylinder or a sphere or some other geometry, these Reynolds number values are going to be different. These are only valid for a flow over a flat plate, flow across a flat plate. Okay, this one has to remember here. So one problem we are going to solve based on this maybe today. Okay. In the today's tutorial. Okay. So here you can see this is the velocity distribution. Again, velocity distribution, one can obtain how my velocity is going to vary in this particular boundary layer. That can be obtained by solving the boundary layer problem. Again, in the turbulent region, here you can see there is a more turbulence present because the eddies are generated. So here there is a eddies are generated, there is a buffer zone, and then there is a small laminar sublayer. Okay. Now let us extend these ideas to heat transfer. So far we were only looking at the flow across a flat plate. Okay, let's extend this to heat transfer.
So can you please explain the meaning of eddies?
So eddies are nothing but there will be a small, swirling of the fluid particles are going to take place. Okay, so that is going to create the turbulence. Is it clear?
All right, sir.
Okay. Now let us look at the thermal boundary, similar to velocity boundary layer, which we have seen in the earlier slide. In a similar manner, there is a temperature boundary layer or a thermal boundary layer is there. For example, let's say the temperature of the fluid stream is T naught, whereas the temperature of this flat plate is, let's say, Ts, and Ts is higher than T naught. In that case, what will happen? The heat will be transferred from this plate to the fluid, isn't it? So initially at the surface, the temperature will be Ts, but as we move along this the upward direction, my temperature is going to decrease, and as I reach to this red line, my temperature becomes same as the free stream temperature, which is equals to T naught, isn't it? So there is a temperature distribution along the upward direction. Okay, so that gives me a thermal boundary layer or a temperature boundary layer. Okay. So here again, one point to note down as temperature boundary layer or a thermal boundary layer and the velocity boundary layer are different. They are not same. But for solving the temperature distribution T, first need to solve the velocity boundary layer, and that you have to input in the energy balance, and then you have to obtain the thermal boundary layer. Okay. So again, one more thing to note down here is the thickness of the thermal boundary layer depends on another dimensionless number, Prandtl number. What is the physical significance? How it is defined, that we will see in a subsequent class, maybe today or maybe next class. So Prandtl number is another dimensionless number which defines the which gives the thickness of the thermal boundary layer. It is defined as nu by A. Nu by alpha. So nu is nothing but the kinematic viscosity divided by alpha, which is the thermal diffusivity. So kinematic viscosity divided by thermal diffusivity is nothing but the Prandtl number. Okay. So again, the important point to note down here is when the Prandtl number less than 1, then momentum boundary layer is within thermal boundary layer. That means the thermal boundary layer is going to have a higher thickness at any location X from the leading edge compared to the momentum boundary layer. Okay, so this thermal boundary layer is going to be higher, is going to have a higher thickness compared to the momentum boundary layer when the Prandtl number is less than 1. When Prandtl number is greater than 1, velocity boundary layer is going to have a higher thickness than the thermal boundary layer. And when the Prandtl number is equals to 1, in that case, thermal boundary layer is going to coincide with the momentum boundary layer. In fact, if you look at a classical case of air, for air, the Prandtl number is 0.69, which is less than 1. But in most of the cases, people consider this is very close to 1. So here you can see the thermal boundary layer and the velocity boundary layer are more or less coinciding with each other, even though the thermal boundary layer has to be slightly above the momentum boundary layer. Is it clear to everyone? Okay.
Yes, sir.
Now, see, so far we have only said that the heat transfer coefficient I wanted to find out, but in most of the cases you will see that the heat transfer coefficient is an average heat transfer coefficient, because that is going to vary as I go across the boundary layer. Even here, as I go across the boundary layer along the thickness of the boundary layer, my velocity is going to vary, and therefore my heat transfer coefficient H is also going to vary. It is not going to remain the same. But when I'm solving a heat transfer problem, there I don't look at the distribution of H. Instead of that, I use a average value of H, which basically incorporate all these, spatial variation inside it, isn't it? So I only look at the average value as I move from this the wall to the free stream velocity here or free stream temperature here. My velocity is going to vary, and therefore my heat transfer coefficient is also going to vary. Okay, but in most of the cases, the average value of heat transfer coefficient is used, because that is going to simplify my heat transfer problem immensely, because I don't have to look at the variation, isn't it? In fact, most of the heat transfer correlations, in fact, all the heat transfer correlations, they report the average heat transfer coefficient. They do not report the spatial variation of heat transfer coefficient across the radius or across the flow across the boundary layer. Let us look at another simple example. So there is a pipe. In this particular pipe, the hot fluid is flowing, isn't it? And this hot fluid is cooled down by a air blowed across this pipe. So this is in a way is nothing but the flow across the cylinder. So here you can see the cylinder, the cross section of the cylinder I am showing here. So along the along the depth of this particular slide, the direction of the flow of the liquid in the cylindrical pipe is there, whereas along the this axial direction, along this, in this particular direction, maybe I show you by arrow, the flow is along this direction. Flow of the air is along this direction. Okay. Okay, so this is a classic case of heat transfer for the flow across the cylindrical surface. Okay, so when this fluid with a free stream velocity V and T naught reaches to this particular point, which is nothing but the stagnation point here, the velocity is zero. Here the velocity is zero, but then the boundary layer is formed, which is shown by a blue lined curve here, isn't it? And within this boundary layer, there is a velocity distribution. So I have shown the velocity distribution, and this velocity distribution is till this point here, which is nothing but a separation point. Beyond this velocity distribution reverses because there is a backflow taking place. So here you can see the velocity distribution is something like this. Okay. So beyond this separation point, there is a backflow and there are eddies formation is taking place. There is a swirling of the fluid is taking place. And beyond this separation point, there are turbulence present in a liquid. Okay. So how the heat transfer coefficient or a Nusselt number, this is another dimensionless number. We will see the physical significance of this particular number, Nusselt number again. This is defined as sorry, I have written NR. This is NU. Sorry, this is NU, Nusselt number. Okay, so Nusselt number is defined as HD by K. We will see the physical significance of this later in the next class probably. So this is dependent on HD by K, where H is nothing but the heat transfer coefficient. Now in this particular figure, we wanted to see how my local Nusselt number NU, varies as I move across this cylindrical surface. So whether how this Nusselt number is going to change as the theta is changing from 0 to 180 and so on, that we wanted to see here. Okay. So as you can see, as the theta increases, that means we are moving along this direction. The boundary layer thickness is increasing. And therefore my heat transfer coefficient H is going to decrease, and therefore Nusselt number is going to decrease. So therefore this Nusselt number is decreasing as we reaches to the separation point, as we reaches to the separation point, the Nusselt number or this HD by K starts increasing because there is a turbulence starts increasing here because of the wake formation, because of this eddies formation, or because of backflow, and because of that the turbulence starts increasing, and therefore my Nusselt number is increasing. Here you can see Nusselt number is defined here as HD by K. Here H is the thing which is H is the parameter which is varying as we are moving along theta. D is constant, which is nothing but the diameter of the cylindrical pipe, and K is nothing but the thermal conductivity, which is also a constant. Okay, so clearly this particular figure also gives me how my heat transfer coefficient H is varying as I move along the theta direction here, isn't it? Okay, so initially it decreases till this separation point, and beyond this separation point it increases because there is a formation of eddies and the turbulence starts coming in. So clearly my heat transfer coefficient H is varying as I move, isn't it? But in a practical heat transfer problem, I don't wanted to make my job complicated. Rather, I wanted to make it more simpler. So one can integrate this H over the theta and then find out the average value of H, and the average value of H can be used for the heat transfer. Okay, is it clear?
Hello, sir.
Yes, please go ahead.
So, what does that backflow account for? Backflow of how?
Remember here, after this point, there will be the movement of the fluid taking place like this. I have not shown it clearly. Remember, after this point, what will happen? There will be a turbulence forming is there, isn't it? And there is a backflow is going to be there because maybe I'll just show you. So I have not plotted it correctly. Okay, so here you can see N type. Just a minute. Just a minute. Let me just do it. Okay. N type. One minute. Okay, I'll just correct it. Can you see? There will be eddies formation which will force the fluid to move in a backward direction here, because here see here there is a pressure drop is going to be there, isn't it, across this cylinder, because the flow is taking place along this direction. Is it clear? The
Yes,
flow
sir.
is going to take place along this direction, so there will be a more velocity here, but here at this location there will be a pressure drop, so flow will be there in the back direction here, and because of that there is a backward velocity distribution here. So that takes place after these separation points. So till this point there will not be any backflow, but here somewhere here at this location here there will be a pressure drop. Is it clear?
Yes, sir.
Okay. Okay, so as I already said that In such cases, the heat transfer coefficient is calculated in terms of some correlations, isn't it? And at that time, I said that uh, this correlation should have some physical, uh, concept behind it. This should not be arbitrary. Of course, nowadays machine learning things are people are doing where it is purely based on the data. But mostly if you look at the correlations used in heat transfer, these are having some physical, uh, you know, backing there. It's not completely arbitrary. So if I'm having a heat transfer correlation in terms of Nusselt number or Prandtl number or Reynolds number, there is some physical backing or some physical principle behind it. Okay, so let us look at one such interesting concept which gives me the information that if I'm looking at the heat transfer coefficient for a particular geometry, what type of correlation or what are the different factors which are going to be there in that correlation. This can be directly obtained using the dimensional analysis. So dimensional analysis is going to give me the information that if I'm looking at the heat transfer coefficient, how this heat transfer coefficient is going to relate with some different factors or different dimensionless numbers. So whether my this correlation should be in terms of Reynolds number or it should be purely in terms of the Prandtl number. This type of information you can directly get by the dimensional analysis. Okay. So let us go through the detail first. Though solving the heat transfer problems became possible due to high-speed computers, the way to solve these easily for approximate result is the use of correlations in terms of dimensionless groups. This is already I said earlier. So the technique of dimensional analysis is a powerful tool to identify the dimensionless group which are used to correlate the variables that influence a practical uh, process, influence a particular physical process. The first step is to identify the relevant variables. This is very important. The first step is to identify the relevant variables, parameters, and the properties. For example, if you are looking at the convective heat transfer to a fluid through a circular pipe, we can say from our experimental findings, and from our understanding.
Sir, your screen is not visible now.
My screen is not visible. I am just making it visible. Just wait. Is it visible now?
Yes, sir.
Okay, thank you. Okay. So we can say from our experimental finding or from our understanding that the heat transfer coefficient H depends upon the fluid velocity V, pipe diameter D, thermal conductivity of the fluid K, its specific heat Cp, density rho, and viscosity mu. So these are the parameters or the variables which are going to be related. So H, V, D, K, Cp, rho, and U are the variables and properties we identify for the purpose of finding the dimensionless group. So here our objective is to find out the dimensionless groups which are going to give me the correlations for the heat transfer coefficient. So for that, the first step is to identify what are the different parameters or the variables that are going to have effect on the heat transfer coefficient. Okay, so in this case for a pipe flow, we can clearly say that the heat transfer coefficient V, heat transfer coefficient H can be related to velocity V, diameter D, thermal conductivity K, specific heat Cp, density rho, and viscosity mu. Okay. So dimensionless analysis teaches us how to cluster two or more of these quantities. So this gives us the information that how these different parameters can be combined together to form some dimensionless groups, and then the correlations can be formulated in terms of the dimensionless groups. Okay. So one of the interesting concept here is a Buckingham pi theorem. Probably you might have done it in your fluid mechanics. Have you? Hello?
No, sir. Not yet, sir.
Not yet. Okay. So even if it is not done in the fluid mechanics, no problem. We will We will try to go through it briefly. Okay, so this theorem states that if the equation phi, which is nothing but the relationship between x1 x2 up to xn equals to 0, is the only relation among the quantities x1 x2 xn, and if this relation holds for any arbitrary choice of units in which these quantities are measured. So what it means is this relation should be a fundamental relation. That is what it says by this particular line. If it holds in any arbitrary choice of the units. Okay, then the solution of this equation has the form again function of pi1 pi2 pi m equals to 0, where pi1 pi2 pi m are the independent dimensionless products of x's. Further, if P is the minimum number of the primary quantities necessary to express the dimensions of x's, then n minus p equals to p. Sorry, n minus m equals to p. So what this particular theorem says, basically, if you are, if you know that there are different quantities and the variables like x1 up to xn, these are related with each other, and that relation holds for any, choice of units, then one can obtain the solution of this equation in terms of dimensionless groups such as pi1 pi2 pi m, where m is the total number of dimensionless groups that can be present in such cases. Again, how many number of dimensionless groups will be required, that you can directly find out by doing a back calculation here. So n is the total number of variables that you already know. Again, based on the dimensions of these particular quantities, you already know what are the minimum number of primary quantities that are necessary. Primary quantities are nothing but the mass, length, time, temperature, mole, current, or luminous intensity. So these are the 7 primary quantities present so far, isn't it? So out of these 7, how many primary quantities are required in this particular case, that you can find out in the starting itself, and based on that you can find out how many dimensionless groups are required to express this relationship. Okay, so let us look at a simple problem here, so that will clarify many things here. So as we have said that for a pipe flow, H is related to velocity, diameter, thermal conductivity, specific heat, Cp, rho and mu. So we have a relationship phi in the bracket HV d k Cp rho mu equals to 0. So that we know that H is related to all these. Let's look at the dimensions of each of these quantities. So H is watt per meter square degree Celsius. So watt again can be defined as joule per second. So joule is again defined as kg per meter square second, second square. So that becomes kg per meter square second cube. So if you put it in terms of watt and rearrange everything, what you get is the dimension of heat transfer coefficient comes out to be mt raised to the power minus 3 and capital T raised to the power minus 1. Here m denotes the mass, capital M denotes the mass, L denotes the length, T denotes the time, and temperature is denoted by capital T. So are you able to get it? Is it clear to everyone? So all these quantities are written in terms of dimensions. Is it clear to everyone?
Yes,
Yes,
sir.
sir.
So here velocity is meter per second, isn't it? So meter will be a unit of length, so that becomes L into T inverse, because per second is there. So per unit time is there. So T inverse. Similarly, diameter is in meter, so that becomes L. Thermal conductivity is watt per meter square, watt per meter degree Celsius. So that becomes ml T raised to the power minus 3 into capital T raised to the power minus 1. Cp is L square T raised to the power minus 2, capital T raised to the power minus 1. Rho is okay. Okay. So rho and mu are also given in terms of dimensions. Now, the next thing is we have, this is the first step, isn't it? We have identified that V, D, K, CP, rho and mu are going to be the quantities on which the H is dependent on. Again, now we have to find out how many are, the dimensionless group we require in this case, isn't it? Because in this case, if you look at the dimensions, there is a mass is present, there is a time is present, temperature is present, L is present, isn't it? So only four, primary quantities are required. Even though there are 7 primary quantities possible, mass, length, temperature, time, then there is a mole, ampere, that is the current, and then there is a luminous intensity. The unit is candela, isn't it? So all these are the fundamental primary quantities, out of which only 4 are required in this case. So my P is 4, n small n is 7. So there are 7 quantities. So 7 minus 4. So that is going to give me 3. So what it means is I am going to have 3 dimensionless groups required in this case. So let us assume that these 3 dimensionless groups are pi 1, pi 2 and pi 3. So these are related something like this. Pi 1, pi 2, pi 3 are related to K, mu, rho, D, H, K, and the exponent here are a1, a2, a3, a4, a5. For pi 2, k raised to the power b1, mu raised to the power b2, rho raised to the power b3, d raised to the power b4, and cp raised to the power b5. Similarly, pi 3 is k raised to the power c1, mu raised to the power c2, rho raised to the power c3, and d raised to the power c4, and v raised to the power c5. So here a1 to a5, b1 to b5, and c1 to c5 are the unknown constants. Again, one more thing to note down here is, see, we have to formulate 3 dimensionless 3 relationships for pi 1, pi 2, pi 3. So here what I have done is I have kept k, mu, rho and d common for all 3, and I have varied h, cp and v, isn't it? But it is not required. You can vary any other 3, isn't it? Since we have only we can have only 3 relations, isn't it? And how many quantities are there? There we are here we are having 7 quantities, isn't it? So obviously 3 are going to vary in each equation, and all other are going to remain the same. So I can have the relations pi 1. Instead of this, I can use here k can be varied and h can be made common. So if I can use h raised to the power a1, mu raised to the power a2, rho raised to the power a3, d raised to the power a4, and k raised to the power a5, and then similarly I can vary k. Here I can vary k cpv, or I can vary the other quantity mu cpv, or I can vary any other 3 I can vary here. There are choices. Out of 7, 3 I have to vary in this equation. So I have selected arbitrarily h, cp and v to be varied across these 3 equations. I have selected arbitrary. This word arbitrary is very important here. It's not necessary that I should use only h here, cp here and v as a variable which are varying across these 3 equations. Okay, is it clear?
So why do we have to vary 5 quantities? Express it in
I have only 3. See, I have only 3 equations, isn't it? I have only 3 equations, and in this case, how many variables are there? I have to make a relation here, isn't it? Correct. I have to make a relation here like this. So if I use this h here, see, if I use the h here also, then these are going to be same, isn't it? I should have all these 3 equations to be different, isn't it?
No, sir, I meant why are we using 5 of these terms instead of 7 or 6 or 4 to represent pi 1, pi 2, pi 3?
If I use, let's say here, you are saying that if I use here a cp raised to the power 6, isn't it? That is what you are trying to say?
Yes, sir, as well. Express it in terms of 6 terms as well or 7 terms as well.
So are you going to get the 3 pi equations after that? If I use, let's say, Cp raised to the power b6 and v raised to the power v raised to the power a7, then in that case we are going to get only one expression pi1, isn't it? I cannot have an independent 3 equations. Did you get it?
Yes, sir. Yes, sir.
So that is why only up to 5 is used. Clear now?
Yes, sir.
Okay. Okay, so these are the 3 equations. Again, the way I have written this equation is not fixed. You can have a variability in this. So arbitrarily you can select any 3 variables which can be varying here across these 3 equations. This particular choice I have done arbitrarily. That is the more important point here. Okay, clear? Can we go ahead? Hello?
Yes, sir.
Is it clear to everyone? Okay. So these are 3 equations. Now let's look at the first equation. Equate all the dimensions of these first equations. So for pi1, the left hand side we have to use the dimensions equals to 0. So pi is a constant, will not have any dimensions. So that becomes m naught m raised to the power 0, L raised to the power 0, T raised to the power 0, and capital T raised to the power 0, and whatever the dimensions of K, U, rho, D, and H are having, that is raised to the corresponding exponents. So here K, the dimension of K we already know. So dimension of K, ML T raised to the power minus 3 into capital T inverse. So that is what is been written here, raised to the power A1. And similarly, all the dimensions are put here. Okay. Now by putting all these dimensions, now we can equate the dimensions here. So mass, the dimensions of mass can be equated to the mass. The dimensions of L can be equated to L, and similarly for T and capital T. So that is what is been done in equation 2, 3, 4, and 5. So here you can see M here is A1. So that becomes A1 plus A2 plus A3. There is no A4 here because there is no mass term here in the fourth quantity, and there is mass term in the last quantity, so that becomes A5. So A1, A2, A3, A plus A5 equals to 0. That is equation number 2. In similar way, we can write down the expression for all other quantities like L, T, and capital T. So this is second equation. Third equation is corresponding to L. So maybe I just do it. This is for M. This is for M. This is for M. This is for L. This is for T. And the last is for capital T. Is it clear to everyone how we got these equations? So by comparing or by equating the exponents, this is what we have obtained. Is it clear to everyone? Yes, no?
Yes,
Yes.
sir. Yes, sir.
Okay, so now equation 2, 3, 4, and 5. How many constants we are having? We are having 5 constants. We are having 4 equations. So obviously we have to express all these 4 variables in terms of the fifth one. So in this case, we are expressing all the variables in terms of A5. Again, this choice is arbitrary. You can select any other. You can consider A2, A3, A5 expressed in terms of A1. Doesn't matter. Okay. So here we have arbitrarily made the choice that we wanted to express A1, A2, A3 in terms of A3, A4 in terms of A5. So from equation 4 and 5, from equation 5, we can directly obtain A1 equals to minus A5, isn't it? And if you put it in this equation, so 3A1 minus 3A5, that is going to be 0. So A2 is going to be 0. So A2 is going to be 0 from 4 and 5. Similarly, from 6 and 7, from equation 2 and 3, we can obtain A3 equals to 0. If you put this A2 and A1 in this, we can obtain A3 equals to 0 and A4 equals to minus A1. So that becomes A5. So this we can just obtain by rearranging the equations 2, 3, 4, 5. All these A1, A2, A3 and A4 we can obtain in terms of A5. So here A2 is 0, A1 is minus A5, A3 is 0 and A4 is A5. So now the relationship we know, pi1 is given by this, pi1 is given by this, isn't it? So A1 we have already obtained, A1 is minus A5, so that is what is put here, minus A5. Mu raised to the power A2, so A2 is 0, so that is 0. Rho raised to the power A3, so A3 is also 0 here. And D raised to the power A4, so that becomes A5, and H raised to the power A5. So if we put all these exponents here, what we get is pi1 is obtained as HD by K raised to the power A5. So this is nothing but the Nusselt number. Remember, HD by K is nothing but the Nusselt number. Correct. So this is the first dimensionless group we have obtained. In a similar manner, we can equate the expressions for pi2. We can equate the expression for pi2. Remember, the expression for pi2 is also there, so we can put the dimensions of all these in this equation, and then in this equation, and then what we obtain is this. So here you can see, if you put all the exponents, all the dimensions here and equate the exponents for mass, length, time and temperature, what we get the expression 8, 9, 10 and 11. So from 8, 9, 10 and 11, again we can rearrange this equation to find out the expression for B1, B2, B3, B4 in terms of B5. Again, the choice of obtaining B1, B2, B3, B4 in terms of B5, isn't it? Because that is varying. Why we are finding out in terms of A5 and B5? That is because in this equation, these are the three quantities which are varying. So that is why these four exponents we are obtaining in terms of A5. These four exponents we are obtaining in terms of B5. And similarly, these four exponents C1, C2, C3, C4 we will obtain in terms of C5, because these are the three quantities which are varying across this equation. Okay, this is not arbitrary. I'm sorry. So this A1, A2, A3, A4 are obtained in terms of A5 because this H is varying in this equation corresponding to the expression 2 for pi2 and pi3. Okay. So from equation 8, 9, 10 and 11, again what we obtained is B1. From 11 we can obtain B1 equals to minus B5. That we can directly obtain here. Similarly from 10, if you put this B1 equals to minus B5 in this, what we get is B2 equals to B5. B2 is same as B5. Again, B1 and B2 we can put it in equation number 8 and we can obtain B3. So B3 is equals to 0. And similarly from 9 we can obtain B4 equals to 0. So that we can put it in the equation of pi2. So this is the expression for pi2. So here B1 is minus B5, B2 is B5, B3 is 0, B4 is 0, and B5 is as equals to B5. So by collecting all the exponents here, what we get is Cp mu by K. So this is nothing but the Prandtl number. And in a similar manner, for the third expression for pi3 also we can equate everything, all the dimensions, and we can obtain the dimensionless group here. So here also we can equate the individual dimensions here. So for mass we can have C1 plus C2 plus C3 equals to 0. That is equation number 10, 12. Similarly for length we will get equation number 13. For time we will get equation number 14. And for the temperature we will get equation number 15. These four equations are rearranged in order to obtain C1. Again, C1, C2, C3, C4 are obtained in terms of C5 because C5 is a dimension of the variable which is varying across. C5 is the exponent of the variable which is varying across the three equations pi1, pi2, pi3, isn't it? So we have obtained all C1, C2, C3, C4 in terms of C5 by rearranging these equations. So that is obtained as B. Sorry. So this is C2. So C2 is obtained as minus C5. C1 is equals to 0, C3 is equals to C5, and C4 comes out to be C5. We can put it in this pi 3 equation, all the exponents, and by putting it in the pi 3 expression, what we get is dv rho by mu raised to the power C5. So from this, what we can conclude is the 7 variables in this problem can be related to 3-dimensionless group, Reynolds number, Prandtl number, and Nusselt number. So clearly, what information we get from this dimensionless analysis is the dimensionless analysis gives me the information that what are the different dimensionless groups which I need to look at when I am, formulating the correlation for the heat transfer coefficient. So for example, in this case, I wanted to make a heat transfer correlation for a pipe flow. So clearly, without looking at the detail, I can clearly say that the heat transfer coefficient for the pipe flow has to be related to 3-dimensionless groups. That is Nusselt number, Prandtl number, and Reynolds number. This information I have got a priori, isn't it? So whatever the experimental data I have generated from the experiments, now I will try to fit all the experimental data in terms of this 3-dimensionless group in order to obtain the correlation, and that particular correlation will be used for calculating the heat transfer coefficient whenever I require the heat transfer coefficient. Okay, is it clear? Can you see the rationale behind the use of dimensionless analysis? Dimensional analysis is going to give me what are the different dimensionless groups that are required for making the correlation for H. I have not said what form of the correlation I'm going to have, but I am definite on the fact that this particular correlation need to have these 3-dimensionless groups. The correlation should have these 3-dimensionless groups, Reynolds number, Prandtl number, and Nusselt number, isn't it? So this information I got a priori even before I have looked at the experimental data, isn't it? So the dimensionless analysis gives me what are the different terms going to be there in my correlation, which I am going to make based on the experimental data. So clearly, whatever the empirical correlations we make it from the experimental data is not arbitrary, isn't it? It's not arbitrary like the machine learning techniques which we do nowadays. It has some basis. It has some fundamental thing behind it. Is it clear to everyone? Hello?
Yes, sir.
So we will continue from this point again. We will go through this problem again in the next class. Okay, I think I have rushed through this analysis little bit at the end, but we will go through again in the next class. So can we stop here unless we have any question? Unless you have any question.
Sir, do we get same three-dimensional group
Yes.
if we represent pi 1, pi 2 in different manner?
Yes. That is what I said in the starting. Yes. Even if you make a different, for example, these three relations, if you formulate instead of H, if you let's say put K here and H constant throughout three, common throughout throughout the three equations, still you are going to get these 3-dimensionless groups. So that is what I said, that the choice of variability of H, Cp and V across these three equations is arbitrary. But one thing you have to note down, whatever the three variables which are varying in this equation, corresponding to that exponent, you have to calculate the other exponent. So here A5, here A1, A2, A3, A4 has to be calculated in terms of A5. That is fixed. That is not arbitrary. Okay. Similarly, in the second case, B1, B2, B3, B4 has to be calculated in terms of B5. But whether I should have H here or K should be there or mu should be there or rho should be there or D should be there, that is entirely an arbitrary choice. Is it clear?
Yes, sir.
you are still going to get the same thing, that you can try to do it with some different setting of pi1, pi2, pi3 and see whether you are getting the same. But I am telling you, you are going to get the same. Okay, but you can confirm it also. Is it clear? Can we stop here unless any more question? Hello. Okay, so we stop here.
Thank you, sir.